Following up on the nucleus, we of course now have to talk about electron arrangement, because in relative terms, electron arrangement is almost even more important, since electrons are the reason why elements tend to react with each other in certain ways. The Bohr model is the one that you're familiar with, the one that you started learning like in elementary school and stuff like that. It's still really useful as an idea of understanding like the distance away from the nucleus elements are. I think the rules that you learned is that there are 7 total rings, so 1, 2, 3, 4, 5, 6, 7. The first ring can only have 2 on it, the second rings can only go up to 8, and then we have 18, 18, 32, 32. The problem is that it doesn't really work. The 288 kind of works, but as soon as we get into that 4th energy level, the 18 really wasn't actually matching up with real results, so more investigation needed to be done. And the discovery of electrons and their arrangements around the nucleus really was contingent on understanding light better. So the thing about electrons is Bohr was assuming that they acted like particles. So they had mass and projections, and he was kind of treating them like they were small balls, like, or you can almost like moons moving around a planet or planets around a sun. But his math didn't work. So what ended up working out is if we combine the idea that electrons are particles, but they're also so small that they actually also behave like light. So electrons actually have wavelengths and frequencies, and the closer they are to the nucleus and the farther away they are, their wavelengths and frequencies change. And by knowing the energy that they have, which is the same thing as saying we know what frequency they have, we can make better predictions about where they are around the nucleus. To summarize that, what we need to remember is that light moves in a series of small pieces called photons, and every photon has a specific wavelength and frequency. They're all moving at the same speed, so the speed of light is 3.0 times 10 to the 8th meters per second. The wavelength, therefore, is in meters, and frequency is in inverse seconds. So what this means is if our constant is always 3 times 10 to the 8th, when we multiply wavelength and frequency together, wavelength and frequency have an inverse relationship. So if waves are really big, it means frequency is really small. If frequency is really large, it can only happen because waves are really small. And what we've learned is the frequency of the wave, or which is also the size of the wave, affects how much energy that wave can carry. So Planck is the scientist who did this. He came up with this number 6.626 times 10 to the negative 34 joules of energy for every measurement of frequency. So that means the higher the frequency, the more energy would be in that photon, which is measured in joules. So let's just pause here and make sure that we understand that. If we're trying to figure out the energy of a photon or an electron, since they move the same way, and we know that there's a wavelength involved, energy does not directly relate to wavelength, it relates to frequency. So we'll have to use both of the equations in order to figure this out. And then we also need to note that speed of light is in regular meters, so that means I'll need to convert my nanometers to regular meters first. So if I assume that the photon is moving at the speed of light and I plug in the adjusted wavelength in meters, I will get a frequency of 4.57 times 10 to the negative 14th. So if I use my Planck's constant, which I just realized that I put the wrong unit on there. Let me go back to this page, right here. It was supposed to be joule times second, because then when you multiply by frequency, which is inverse second, the s's would cancel out to leave you just joules. My bad, I accidentally wrote joule/second earlier. So if we go back to this, okay, we'll use Planck's constant for every second worth of frequency. We'll have this many joules. So these two numbers multiplied together, I ran out of space. Actually, I just want to write that more clear. So here's our Planck's constant, here's our frequency. Seconds times inverse seconds is going to cancel out, which leaves us with an energy of 3.03 times 10 to the negative 19th joules. Okay, so bringing this back to electrons, what does this all mean? So basically what we ended up finding out is that we could measure the wavelengths and frequencies of electrons and how much energy they had, and that was giving us an idea of where they existed around the nucleus of an atom. So we now have this adjusted model called the quantum mechanical model. So remember, quantum is referring to how much energy do the electrons have, because that determines what level they're on and what kind of orbital they're in and how many other electrons they're near. This model is a lot more complicated than Bohr's model. These are not to scale at all, but basically what this picture does show you is there are 4 types of orbitals that electrons can mathematically exist in. We have what we call S, P, D, and F orbitals, which correlates to what you have seen on your periodic table with S block, P block, D block, and F block. Where those elements are represents where their last electrons are filling in. Are they filling in p orbitals, d orbitals, or f orbitals, or s orbitals? So it looks a little bit like this. So you'll see hydrogen and helium up here. They have electrons in the 1s area, and then the last electrons for lithium and beryllium are in the 2s. But then boron over through neon, those last electrons are in 2p, and it continues on and on. So we can use the periodic table to summarize the location of all of the electrons in an element in a much more accurate way than the Bohr model allowed us to do. So rather than drawing the Bohr model of hydrogen with the nucleus in the middle and a ring and 1 dot, what we're going to say is that electron, we want to say how far away it is from the nucleus, what kind of orbital it is, and how many electrons are in that location. So since hydrogen is on period 1 on the periodic table, I'm going to use a big 1, and then I'm going to say it's in S block, so it's in that kind of orbital, and there's only 1 electron there. So the big number represents the energy level. Energy level. This represents the type of orbital. And then the superscript is the number of electrons in that spot. If we use beryllium as our next example, okay, instead of drawing it like this, what we want to say is more specific information about those 4 electrons. So the first 2 electrons are always in the very center of, like, right around the nucleus, and that's going to be where hydrogen and helium's electrons are. So we always start electron configuration with hydrogen because that is the very first electron that is added to every single element. So that means that for beryllium, the first 2 electrons are on level 1, they're in S block, but there are 2 of them. We need to change up what we're writing because when we get to the next 2 electrons, something has significantly changed, which is that we've changed energy levels. They are now on energy level 2. They are still in S block orbitals, just not the same S block as the one that was on level 1, and there are 2 of them. So what we're saying here is we have 2 electrons on level 1 in an S-type orbital, and we also have 2 electrons on level 2 in an S-type orbital. If we continue on to nitrogen along the same path, remember we're always starting with element 1, so the hydrogen and helium electrons are 1s2, the lithium beryllium electrons are 2s2. When we cross over to boron, what we are changing is not the energy level. We're still on energy level 2, but we've now entered new orbitals. So we now have p-type orbitals, and we're going to go 1, 2, 3 over. So let's talk about that for a second. So what we're saying here is nitrogen has 2 electrons on level 1, and it has a total of 5 electrons on level 2. But 2 of those electrons are in an s orbital and 3 of them are in p orbitals. So one last time just for clarification, let's do all 40 of calcium's electrons. The first 2 are always on the first energy level in an s block orbital, and there can only be 2 of them. The next 8, 2 of them are in an s orbital and 6 of them are in the p orbitals. And then if we keep going, we see that we have a level 3, we go back to S block, then we have sodium, magnesium. Okay, then we carry on, still on level 3, but now we switch back to P block, aluminum, silicon, phosphorus, sulfur, chlorine, argon, that's 6 again. And then the last 2, the most important 2, are level 4, S block, there's 2 of them. So this is 2 plus 2 plus 6 plus 2 plus 6 plus 2. This is all 40, what am I talking about? 20, because I can count, this is all 20 of calcium's valence electrons. Now let's talk about the weird exception to the rule when we get into D and F blocks. So let's say we were continuing right past calcium to titanium. Well, we know that the trend is that they're all the same until they get to the very end. So the first 20 electrons of titanium's 22 are going to look exactly the same as calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Awesome. So what you would expect is that the next two would be like, oh, they're on period 4, but now we're in D block and there's 2 of them. And here's the problem. They're not on level 4. The issue with this section on the periodic table and with eventually with F block is for whatever reason these electrons always register at a level lower than what the periodic table lists them on. So what we need to do when we get into D block is we're going to have to decrease 1 from the energy level. So these last 2 electrons are secretly on level 3. They're actually not on level 4. So just one more time with that. Let's do 10, which is way down here. I'm just going to save some space and skip ahead for a second. Let's say we pick up at 5s2. So what we need to remember is that these next electrons are technically not on level 5. They are actually 1 level lower, 4d, and if you count all the way over, there's 10 of them altogether. But then what we need to remember about the last 2 electrons is that they are in p orbitals, which are at normal energy. So that means our last 2, we're going to put them back on level 5, p2. So now what you can see here is what would have looked like 10 having 14 valence electrons. Level 4 is not the same as level 5. So 10 really only has 4 valence electrons. It has 2 in an s orbital and 2 in a p orbital. All of these electrons that happen as we transition across D block are technically on level 4. Now F block gets real funky. So again, I'm going to go ahead and skip ahead and just say that I stopped at xenon here and we're going to pick up at 6s2. So here's the thing. You get to LA and you're like, oh, I'll do 5d1. Awesome. I just learned how to do that. And then the next thing that happens is all of a sudden there's this huge transition. So the reality is that in order for you to get all the way across to lead, even though you fill in this 1 electron right here, you have to go all the way across F block before you can finish D block. So what we're going to do is we're going to go ahead and include that 5d1 with the rest of its kind after we finish F block first. The other fun thing about F block is it has even less energy than the D block that came before it. So instead of this being 5F, this is actually 4F. So you have to subtract 2 from the energy level. So we're going to do 4F. So CE all the way through LU is 14. Then we come back up to LA and we're going to do LA through gold, which is now 5D10. And then we get to finish with those last 2 electrons, which are back on their original energy level, 6p2. So these are the 4 electrons that would actually be considered valence electrons, but there's 24 electrons that come in between those 2 sets. Let's look at this a little bit